Hello everyone. So in this video we are going to perform a linear static analysis on this I-beam. As you can see, I have a meshed model of this I-beam. So if you want to make the exact model, you can go to my blog post and check the dimensions of this model. Okay, so without wasting time, we'll start with the process. So first of all, we need to prepare a model, or we need to have a model on which we'll perform the static analysis. Then we need to assign the material for the model. So to do that, we'll go to this left browser area, right click on it, go to create, and we'll select material. So for this tutorial, I'll be using steel. Okay. So the value for steel are present by default here. You can see I'll just click enter. Okay. Then as you can see on this screen, this is a 2D element, 2D mesh. So you have to assign shell thickness to this material, shell thickness to this mesh. So we'll right click on the browser area and go to create, and we'll select properties to assign the thickness. So we'll name it as shell property. The card image will be P shell. Material will use here as steel, and the thickness for this we'll put as 1.2 mm. Okay. Now we'll assign this material and shell property to all the components of the mesh. So this top flange will assign the property shell property. Okay. Bottom flange also will go and assign the property shell property. Middle section also will assign the property shell property. Okay. Now we have a mesh ready. We have assigned the property and we have assigned the material to the mesh. So the next step would be to assign the boundary conditions. So for this tutorial, we are going to fix both the end edges of the I-beam. So for that, first we'll create a load collector to assign the constraints. So we'll go and right click on the browser area, go to create, then select load collector. So we'll name this constraint. Okay. Now to create this constraint, we have to go to analysis. We'll go to constraints. So basically what constraint we are going to apply here is we're going to fix all the degrees of freedom of both the end faces. So for that we'll select the end face nodes. So we'll go to by path, you click okay. Okay. So we have selected all the nodes on the end face. So all the degrees of freedoms, as you can see, the degrees of freedom are selected. The values assigned are 0. So we'll click create, and this will fix all these nodes on the end faces. As you can see, 1, 2, 3, 4, 5, 6, all degrees of freedoms are fixed. Similarly, we'll select the other face, nodes on the other face. We'll go to by path. And we'll check all the degrees of freedom and we'll assign the value 0 and we'll click create. So as you can see, both the end faces are fixed now. Okay. So we'll return back now. And to apply the load, we'll click Again go to the browser window, right click and click go to create and select a load collector, and we'll name this load collector as load, since we are going to use this to store the load. So to apply the load, we have to go to analysis, we'll go to forces and select the nodes through which the load will be applied. So in this case, we are going to apply uniformly distributed load on the top flange. So we'll select one node and we'll go by phase. Okay. Selecting the bottom face also. So what we'll do, select the top, select the nodes on the top flange. Okay. So as you can see, the nodes on the top flange is selected. Okay. Then we have to assign the magnitude of the force. So here, as you can see, the magnitude, we have option to assign the magnitude. So we'll be assigning the magnitude in negative y direction. So let's suppose we'll apply a force of minus 10 Newton on each node, type minus 10. So the minus sign here signifies that the force will be pointed in the opposite direction. Okay. So load type is force. Relative size is the display of the arrow of the load. You click create. As you can see, the load is created and 10 Newton of load is applied on each of the nodes. Okay. So now we'll click on return. So we have created the mesh, we have assigned the materials and properties, we have created the boundary condition. Okay. Now after this, to run the analysis, we have to do one more step. We have to create a load step. So we'll go to the browser window, right click there, select create and go to load step. Okay. Now we'll name this suppose static. So as you can see here in the name value window, so the analysis type here is generic. So we'll change this to linear static. Okay. So now we have the option here to select SPC. So SPC here is basically single point constraint. Here you have to select the constraint load collector. So we'll select constraint here. Okay. Then load, we have to select the load collector. Select load. Okay. And rest of the things it's not needed. So we have basically selected everything now. We have made the mesh, we have assigned the material, we have assigned the property, we have created boundary conditions, and we have assigned those boundary conditions inside load step. Now the next step would be to run the analysis. So for that, we'll go to analysis and we'll go to Optistruct. So in this tutorial, we are running this, we are solving this through Optistruct. We have other solver options also like Nastra and Abacus, but for this tutorial, we are going with Optistruct. Okay, so we'll go to analysis, we'll go to Optistruct. So just in case if Optistruct is not visible here, you can go to preferences, user profiles, and you can select Optistruct from here. Okay. So we'll go to analysis, Optistruct. We'll name the file, give the file an appropriate name. Okay. Then export options will keep as custom. Run options will make it analysis. Okay. Memory will keep as default, and then we'll click on Optistruct. So once you click on Optistruct, a pop-up window will open, as you can see here. It will show the progress of the solver. So this is completed now. This was a uh, very short or very easy analysis. It's completed now. So this kind of pop-up window will open, and here you can see input file job is completed now. So message log analysis completed. Optimization summary. Okay. So this means the solver was run successfully without encountering any errors. Now to view the results of this analysis, to visualize the results, we have to click on results. Besides that, there is a view option here. So if you click on the drop down, just adjacent to the view option, you have the option to see the output files. It will contain the data about the run. Okay, so moving on to visualizing the results, you click on results. So once we click on results, a new window opens. So this is the hyper view window. In this we can basically see the results of analysis. So to see the results, click on this, then we'll click on apply. So this basically gives us the displacement. So we'll change it to stresses and we'll click on apply. Okay, as you can see, this is how the stresses will look like on the beam. So the stresses are showing to be maximum in the central area. As you can see, this red and orange area. So this is the legend which shows the magnitude of the stresses adjacent to the colors, indicates the value of the colors. So as you can see, these red areas, the value is 2.14 into 10 to the power 3. The least here it's 1.825 into 10 to the power 1, that is 18 megapascal. So one more thing to note here is all these values are in megapascal. Okay, so clearly this 2.14 into 10 to the power 3 indicates that the beam is failing at those areas. Okay, so this is how you can know where the beam is failing, where the maximum stresses are there, and where do you need to provide stiffness or strengthen the beam, or where do you need to make changes to the structure in order to make it sufficiently strong. Okay, so this is all for this video. I'll be making a separate video on Hyperview and how to use it to get most out of your results. So this is all for this video. Thank you. Please like, share and subscribe.